Hello, I am Halter Mataifa, and this is a lecture on the frequency response analysis of control systems. Starting with the simplified block diagram representation of a control system modeled by a transfer function, we see that it is basically a characterization of the system as a ratio of the Laplace transform of the output signal C of S and the Laplace transform of the input signal R of S, which we call the transfer function of the system. One form of representation of the transfer function is as a ratio of products of factors in the Laplace variable S. The numerator factors are referred to as zeros of the system, and the denominator factors are the poles of the system. So given the transfer function model of the control system, we can analyze the system's behavior either in the time domain or in the frequency domain. The time domain analysis enables us to look at the system's transient and steady state behavior for various types of input. And since most control systems are typically modeled as position control systems, time domain analysis often takes the form of a step response of a system. So given a control system represented by a block diagram like this one, if we apply a step input, a typical output may be given by a graph that looks like this. The output response provides information about the stability, transient, and steady state behavior of the system for the given input. If an analytical expression of the time domain response is required, then we need to take an inverse Laplace transform of the system. A control system can also be analyzed by means of the root locus technique, which is a frequency domain analysis method done in the Laplace domain. The stability and transient response behavior of a system in the Laplace domain is determined by the location of the closed loop poles in the S-plane. And the closed loop poles are essentially the roots of the characteristic equation 1 plus g of s, h of s equal to 0. Now on the S-plane, we have already discussed that the requirement for closed loop stability is that all closed loop poles lie on the left half plane of the S-plane. Further, the precise locations of the closed loop poles determine such parameters as the damping factor and the undamped frequency of oscillation, and thus also dictate the transient response characteristics of the system. The root locus technique allows us to see how variations in system loop gain affect the location of the closed loop poles, which in turn affects the system's stability and transient response. It also enables us to design a compensator so as to improve the overall control system response. Frequency response analysis is another method that provides very useful tools for stability and transient response analysis, as well as compensator design for control systems. So basically, in the frequency response analysis, instead of applying a DC signal, such as a step input, to analyze the output response characteristics, we apply a sinusoidal input and analyze how the system responds to this input. What we find is that for a linear time invariant system, such as we are considering, both the shape and the frequency of the input and output signals are pretty much the same. The difference will be in the magnitude as well as the phase of the output relative to the input. This difference is dependent on the type of the system as well as the frequency of the input. This leads to the characterization of the frequency response analysis of a system in terms of how the output waveform's amplitude and phase relate to the corresponding values of the input waveform. So we see that in the frequency response analysis, the system transfer function can be represented as a two-term variable: the amplitude response, m, and the phase, phi, which are both functions of the input sinusoid's frequency, or omega. The main interest in frequency response analysis is in evaluating how the amplitude as well as the phase respond in the steady state as the input frequency is varied. So the definition for a frequency response of a system essentially consists of two components. The magnitude response is the ratio of the system's input sinusoid amplitude to the output sinusoid amplitude, and is given by this ratio. The phase response is the difference between the phase of the output waveform and the phase of the input waveform. So we note here the important point that the magnitude and phase responses are both functions of the input frequency, and so we are able to analyze how these two quantities change as the frequency is varied, say from 0 to infinity. So in this lecture we will look at two main frequency response techniques. We will look at body plots as well as Nyquist plots. And it is useful to keep in mind our objectives in this analysis. We want to determine the closed loop stability of a system. Then we want to design a control system so as to have sufficient relative stability and satisfactory transient and steady state performance. So we use these two techniques, the body plots as well as the Nyquist plots, in combination to achieve this. A sinusoidal signal is defined by three main parameters: the amplitude A, the frequency omega, and the phase theta. Here we assume that the phase is equal to 0 degrees. Now if we take this to be our input to the system, which can be represented in the Laplace domain, because the system is also represented in the Laplace domain, we find that the output response will consist of a transient component as well as a steady state component. The frequency response is determined based on the steady state sinusoidal response of the system. The Laplace variable S is a complex variable having a real component sigma and an imaginary component omega. If we take S to be purely imaginary by letting sigma to equal to 0, then the complex function of S is essentially transformed into a function of the frequency omega. So analytically, the frequency response analysis amounts to substituting S with j omega in the transfer function of the system. Then the steady state frequency response will be given by the product of the input sinusoid R of t and the transfer function g, with S being replaced by j omega. Evaluated at a given frequency, this frequency response function will consist of two components, the magnitude as well as the phase. And so the output will be a sinusoid whose amplitude is the product of the input amplitude and the transfer function amplitude, and the phase is going to be the sum of the input phase as well as the system phase. In this case, since we took the input phase to be 0, the output phase corresponds to that of the system. Now, before getting into the frequency response analysis, it is useful to review some complex arithmetic, which will be very relevant to the subsequent analysis. A complex number z can be represented in the complex plane as having a real component x and an imaginary component y. And this can be written as a sum of the two components, with the imaginary variable j being associated with the imaginary component y. This j is basically a representation of the square root of -1. This is referred to as the rectangular form of a complex number. It can also be written in the form of sine and cosine terms based on the trigonometric relations in a right-angled triangle. In this case, the modulus of z is given by the square root of the sum of the squares of the real component and the imaginary component. And the phase is given by the arctangent of the ratio of the imaginary component to the real component. These formulae play an important role in determining the frequency response of a system, which basically consists in calculating the magnitude and phase of the system at a given frequency. Two other useful forms of representing a complex number are the polar form and the exponential form. So given a complex number z, we find its complex conjugate by simply reversing the sign of the imaginary component. This is very useful when trying to normalize a complex rational number, as we will see later. We can add and subtract or multiply and divide complex quantities just as we do in the case of real numbers. So if z and w are two complex numbers represented either in the rectangular or polar form, they can easily be added or one can be subtracted from the other, and this is easier in the rectangular form. For instance, if r is the sum of z and w, then the real component of r is the sum of x and u, which are the respective real components of z and w, and the imaginary component is the sum of y and v, which are the respective imaginary components of z and w. To determine the product of z and w, we can either do it in the rectangular form or in the polar form. In this case, the polar form tends to be more convenient, since it simply requires multiplying the amplitudes and adding the phases of the respective numbers in the polar form. We can also determine the quotient, or we can divide one complex number by another one, and this is also more easily done in the polar form, where we divide the two magnitudes and find the difference of the phases. In frequency response analysis, we often encounter situations where we have a complex fraction and we desire to separate the imaginary component from the real component. We can achieve this by multiplying both the numerator and the denominator by the complex conjugate of the denominator of the fraction. When we expand this, we end up with a real number in the denominator, and this allows us to separate the real component from the imaginary component. Let us look at an example. So we are given here the transfer function 1 over s plus 2, and we are asked to determine the frequency response function. Dealing with a problem like this, we want to keep in mind that a frequency response function is basically comprised of two components: the amplitude and the phase as a function of the frequency. So the first step is to substitute s by j omega, and then to determine the amplitude and the phase. Now the transfer function that we have here, in order for us to be able to determine the amplitude and the phase, we need to split it into the imaginary component and the real component according to the formula for the magnitude and the phase. So we do that by multiplying, by normalizing it, multiplying both the numerator and the denominator by the complex conjugate of the denominator of this frequency response function. And when we do that, we are able to separate the real component from the imaginary component, as we have here. According to the magnitude response formula, we find it by taking the square root of the sum of the squares of the real component and the imaginary component. So when we do that and simplify, we end up with the expression 1 over square root of omega squared plus 4. We likewise determine the phase response using this formula, and when we simplify that, we end up with the expression negative arctangent of omega over 2. It is important here to note that signs of the real and imaginary components should be taken into account when we are looking at the phase response of the system. So in this case, the imaginary component is negative and the real component is positive, and this leads to a situation where the output lags behind the input. In the next example, the input is given as well. So in addition to calculating the system frequency response, we also have to determine the output frequency response for the given input. The procedure for calculating the system frequency response is similar to the previous example. So we make the substitution s equal to j omega, and normalize it by multiplying both the denominator and numerator by the complex conjugate of the denominator, and then we can split that into the real component and the imaginary component. So the magnitude response term is given by this. So this is 4 over square root of omega squared plus 1. Now from the given input, we note that the input frequency is equal to 3. So we can substitute this into the magnitude response, and we end up with the value 4 over the square root of 10. Similarly, we make the substitution in the formula for the phase response, and after simplifying, we find that the phase is equal to negative 71.6 degrees. Then the output, we can determine the output by finding the product of the input and the frequency response function. So from this product, we can see that the system will cause the input to be amplified by this factor 4 over the square root of 10, and it will cause the output to lag behind the input by 71.6 degrees, because the phase in this case is negative. The final expression for the output has got an amplitude of 2.53 and a phase of negative 11.6 degrees, and we can see that the frequency of the output is the same as the frequency of the input. In the next example, we look at determining the frequency response for a given range of frequencies. So using the procedure from the previous examples, we can determine the frequency response function and then evaluate it at the frequencies given here, omega equal to 0, 2, 10, 100, and infinity radians per second. So the first step is to determine the frequency response function, and using the previous procedure, we find that the magnitude is equal to 3 over the square root of omega squared plus 4, and the phase is negative arctangent of omega plus 2. So we can evaluate this then. We can evaluate these two expressions at the given frequencies, and when we do that, we end up with a table that has values of magnitude and phase corresponding to each frequency. So this is the table. For each frequency, we've got a value of magnitude and a value of phase. Looking at the table, we see that the effect of increasing the input frequency is to attenuate the input magnitude, because the magnitude progressively decreases as the frequency increases. We also see that the phase lag increases with the increase in frequency, and it tends to 90 degrees as the frequency tends to infinity. So this system is an example of a low pass filter, because it attenuates signals of high frequency while having a minimal effect on the signal in the low frequency range. We will now look at an alternative method for determining the frequency response function, which could sometimes be easier to apply than the one that we have been looking at. Here we look at a transfer function 1 over s plus 1, and we need to determine the frequency response for an angular frequency of 1 radian per second. Using the previous method, we find that the frequency response is given by this value here, 1 over square root of 2 at an angle of 45 degrees. Now if we consider the pole 0 plot of the given transfer function 1 over s plus 1, it only has one pole, which is sitting at negative 1. And if we draw a straight line from this pole to the input frequency, which is equal to 1, and it is going to be sitting on the j omega axis, we find that this line has a magnitude of a square root of 2, and it makes an angle of 45 degrees with the positive real axis. And this can be written in this form, because we see that this is a pole which sits in the denominator of the transfer function. So looking at this, we see that we arrive from this procedure, we arrive at the same answer as we had using the previous method. And so we can use the pole 0 plot method as an alternative to finding the frequency response of a system. Now, to apply this method, we begin by drawing the pause zero plot of the transfer function and marking the point on the j omega axis that corresponds to the input frequency. Then we draw straight lines from each of the poles and zeros of the transfer function to the point on the j omega axis, and then calculate the magnitudes and phases of all the lines. From this, the magnitude response is given by the product of the zero magnitudes divided by the product of the pole magnitudes. The phase is the difference between the sum of the zero phases and the sum of the pole phases. So looking at this example, we can use this procedure to determine the frequency response function of this transfer function, as well as the output given this input. In line with the procedure outlined in the previous slide, we begin by drawing straight lines from each of the poles and zeros of the system to the value 2, which corresponds to the input frequency of this. Then we determine the magnitudes of each of the lines, as well as the angles that they make with the positive real axis. From this, we can determine the magnitude to be the ratio of the magnitudes of the zeros divided by the magnitudes of the pole lines, and we get the value 1,265. Similarly, we sum up the zero angles and subtract from it the sum of the pole angles, and we get the value 18,435 degrees. The next thing is to determine the output, and we do this by multiplying the input by the frequency response function. And when we do that, we find that the amplitude of the output is 12,65. It's got a phase lead of 18,435, and its frequency, as we expect, is the same as that of the input. So we can say that this system amplifies the input, and it causes the output to lead the input, or the input to lag behind the output. Sometimes we have to consider a transfer function, and it can be considered to be a cascade of a number of subsystems. So, for example, given this transfer function 1 over s plus 1 to s plus 1, this can be considered to have two subsystems, which can be represented this way. And it may be convenient sometimes to consider these two subsystems separately, and we use the rule that the magnitude of the product, so given two complex functions or numbers z and w in polar form, the magnitude of the product is the product of the magnitudes of the two complex numbers, and the phase is the sum of the separate phases. So this can simplify the analysis of a complicated transfer function, where we can break it up into subsystems. So where possible, we could break up a complicated transfer function into a number of subsystems, and then we know that the magnitude response of the transfer function will be the product of the magnitudes of the respective subsystems, and the phase will be the sum of the respective respective phases of the system. Okay, so in the next session we will be looking at body plots, which is one of the frequency response analysis methods that we are going to be using. Thank you for watching. See you in the next session.